Log on, tune in, find out. Another good idea from Cambridge.
Statisticians, whom I used to meet very often at control engineering conferences, who publishes a lot in control engineering journals, but he's a bright statistician first of all. So it's Luc Pronzato from India, from CNRS in Sofia Antipolis.
Thank you, Darius. Thank you for the introduction and the invitation, and thank you for giving me the opportunity to give this talk here. So I'm going to speak about adaptive design and adaptive control and the connections between the two. And so the outline of the talk is as follows. First, I will recall some well-known results about the design of optimal inputs for dynamical systems. Then I will speak about adaptive control and show some of the difficulties in adaptive control and how they are related to the asymptotic properties of estimators. And of course, this will be connected with problems in sequential design. And so I will consider in particular the optimal design and penalize the optimal design. And we shall see that penalize the optimal design can be used to solve some problems in adaptive control. I will present some examples, probably just one because of time limitation. Then I want to say something about design problems where we have some dynamical constraints on the design itself. And of course, it will be connected with the first part, but we shall see some of the difficulties that we have there. So, optimal input design. So the design of optimal inputs for dynamical systems. So this is all well known. I mean, this you see rather old. It started in the early 70s. And it concerns a case where we have a linear dynamical system. So it's not a regression model, but it's sort of a regression model where xk, the design variable, may depend linearly on a lot of things. It may depend on previous observations, on previous inputs. So uk will be the sequence of inputs. So it may depend on previous inputs, and it may also depend on previous disturbances. And the objective is to choose the sequence of inputs here to estimate theta the most accurately possible. So I will denote by M the information matrix, and the input sequence I will denote it by xi, because then I have the same notation all over the talk. So here it will be mainly an algorithmic problem, that in the sense that we have to construct the information matrix and then we have to optimize it with respect to the input sequence. And I will take some examples. I will consider some examples. The first one is a case of a finite impulse response model. So if we use the notation with the Z transform, we say that Y is BU, with where B is a polynomial in Z minus 1, and Z minus 1, you can think it is the time delay operator. So this is just, in fact, a condensed form for this expression that says that Y is a linear combination of previous inputs, plus some additive noise. Okay. So we want to choose, for instance, the input sequence to estimate the coefficients here, the BIs, and we set some constraints on the input power, on the power we put on the input. So here, in fact, we have a linear regression model. So this is a regressor, and you see that we have a sort of dynamical constraint on the regressor, because this is just a shift register on the input. And we want to have a precise estimation. So here the variance of the least square estimator is proportional to R transpose R minus 1, with R is a matrix which is constructed by the sequence of regressors. We construct R transpose R, and so we have, for the optimal design, we maximize the determinant of R transpose R, and we see that the optimal U should satisfy this type of conditions. For a large N, it means that the white noise sequence will be satisfactory. So this was the first example. A second example, which is a little bit more difficult, is the case of a model with an autoregressive part. And we consider the most general form of this, which is called the Box and Jenkins model. So again, with the Z notation, we have Y, which is Fu plus J epsilon. So F and J now are rational fractions in Z minus 1. So this just expresses that Y is obtained by a linear filtering of U and plus a linear filtering of the epsilon. Yes? So we make some assumptions here on F and J and so on, but this is not very important. This is just to give you the feeling of how it works. So we have this. The first thing, we need to construct the information matrix to estimate the parameters here and here, yes? The parameters theta. So why that? Because if we have a suitable input sequence, which has the property of what is called the persistency of excitation, then asymptotically, the maximum likelihood estimator will be distributed with will be normally distributed with an asymptotic variance which is proportional to the Fisher information matrix. So we want to construct the Fisher information matrix, and then we will try to optimize some scalar function of it. So the definition is there. So we need to compute first the log likelihood. To do that, we first construct what is called a prediction error. So EK corresponds to the error epsilon k when theta is the true value of the parameters. So we construct this, and from this we construct the log likelihood of the observations. When we have done that, well, we simply differentiate this. We use some properties, the independence of two errors at different I and j. We use the property that the errors are assumed to be normal and so on. So doing this, we arrive at an information matrix which is block diagonal, with one block related to the estimation of sigma square and one block related to the estimation of the parameters in f and j. And this block can be written like this. Okay. Next, because we had the expression of the prediction error, we can differentiate it. And then we use some properties like, for instance, that f and j, the block f and j, have no common parameters. And also we have an open loop identification. It means that there is no closed loop, which means that there is some independency between the inputs and the prediction errors. And if you do the computations using all this, you arrive at the fact that this matrix here is itself block diagonal, with one part in red which is related to the estimation of the parameters in f, and one part in blue here which is related to the parameters in j. And in fact, U only appears in the red part, which means that U cannot be used, U cannot help to estimate the parameters in j, because j is just the transfer from the disturbances to the output, while f is the transfer from the input to the output. So U can be used to estimate the parameters in f, yes? And this is the expression of this matrix. If we want to construct a d-optimal design, then we will maximize the determinant of this matrix because it's block diagonal. We cannot act on this one, so we simply maximize the determinant of this one. Okay, so we want to choose an input sequence that maximizes this determinant. Now, this matrix here, the red matrix, which was there, so we can write it in this way, where now the vector f here, it's a sort of regressor if you want, but it can be written like that, and it is obtained by a filtration of the input sequence. So again, we have a sort of dynamically constrained design problem, because this is the usual form of an information matrix, but you have a special form for the regressors inside. So how to find the optimal input sequence now? Well, you have to find the sequence of U's that maximizes this determinant. So this is completely deterministic. So it's not a statistical problem. It's purely an algorithmic problem. But so it's an optimal control problem, but it is highly nonlinear because the determinant of this is completely nonlinear. So it's a nonlinear control problem, which is not trivial. But okay, this is. So it's even more complicated if you have a nonlinear dynamical system, because then the construction of the information matrix itself is more complicated. So this type of problems is not very easy to solve. There is a simpler solution if we can have an online characterization of the parameter uncertainty, which means if we use a recursive estimator, then we can work one step ahead. Yes? So this is now the idea here in this third example. Assume that we have an autoregressive model. So again, here I use the Z notation, but this only means that yk is a linear combination of previous y's and previous u's plus some additive noise. Yes? So this is the condensed form for this equation. Okay. So in this case, we can use, for instance, Bayesian estimation with a recursive least square estimator. And we know that in the recursive least square estimator, we have a recursion for the posterior covariance matrix of the estimator. This is simply the recursion that is used in recursive least squares. So pk is the posterior covariance matrix for theta. So pk plus 1 is after we have observed yk plus 1, and so after we have applied uk. So we have this recursion. If we want a d-optimal design, we want to minimize the determinant of the covariance matrix. So we minimize this determinant using this. Well, we do the calculation. But this is well known. We can express this determinant in this way. So we want to minimize this. So we want to maximize this. And if you look at this expression here, because f is written like that, this thing will be quadratic in uk. Here it was fk uk minus 1, so fk plus 1, it will be uk, but it's quadratic in uk. So we want to maximize this function, which is quadratic in uk. It is also a convex function in uk. So if you set bound constraints on uk, it's a quadratic. It's quadratic and convex, so you know that the optimum is at one of the endpoints. You simply have to choose one of the endpoints, look which one gives the best result, and you apply this. So it's very easy to implement. So in this case, the solution is very easy. But this is just one step ahead, because you're just looking one step ahead. Nothing says that the sequence you construct in this way will be an optimum, because you're just optimizing the next, the value of the next covariance for the estimator. Okay, so this is the type of results we have for optimal input design. You see, it's not there is not much statistics there. It's mainly some algorithmic problem. We can also work in the frequency domain. Since you remember, for instance, for the Box and Jenkins model, the Fisher information matrix for the estimation of the parameters in F can be rewritten in this way, with F is a vector obtained by a filtration of the input. You remember that. Now, if we consider the average Fisher information matrix per time unit, and if we use a uniform sampling, so we have this matrix here, which is the limit of this matrix divided by t when t tends to infinity. So using Parseval's theorem, we can write this matrix in this way, where now this is the power spectral density of this quantity here. Yes? And using a property of linear filters, this is nothing but the integral now of a function of some matrix multiplied by the power spectral density of u now. Yes? And so we get this expression. And those who are familiar with approximate design theory, we recognize immediately that here we have some sort of design measure. So we are exactly in the same framework as in approximate design theory. So now the experimental domain is the frequency domain. The design measure is the power spectral density of the input signal. Yes? And because we know that the optimal design corresponds to a discrete measure, in here the optimal input signal would correspond to a signal with a finite number of frequencies. So we have a combination of sinusoids. Yes? So the support point gives the frequencies, and the weights correspond to the power which is set on every frequency. So we are exactly in the same framework. We can use the same algorithms as for approximate design theory, but in fact there is no approximation there because here, because the weight is a power, you don't need that the weight should be some rational number. You have no restriction. So it is approximate theory, but there is no approximation. Okay, so again, this is an algorithmic problem. We can solve that, but this is only for linear systems because we went to the Fourier domain, and so this only works for linear dynamical systems. Okay. Now I'm going to the second part, which is about an adaptive control. We'll see that here we have some statistical problems. Consider again an autoregressive model. So you remember that it means that y is a linear combination of these quantities here. And assume that we want to solve what is called a self-tuning regulator problem, which means we want to find a minimum variance controller. That is, we want to minimize the regret here that has this expression. So we want to find a sequence, an input sequence that minimizes this. And the definition which is used is that an input sequence is, say, globally convergent if Rn divided by n tends to 0. So we want to, so that in fact, the output should be should be close to 0 in the sense that the only difference from 0 should be due to the noise. Yes? We want to regulate the system so that the output is 0. Okay. So if we know theta, if we know the value of the parameters, well, then it's rather easy. You simply need to have f transpose theta equal to 0, and then what you will have here will be just the noise. And when you subtract the noise, you will have 0, so everything will be fine. So if you know theta, you know exactly what to do. So if theta is known, you simply use uk at time k with a function of theta, which is given by this. But you see, of course, you need to know all the coefficients here. So you need to know the parameters to apply this. The problem is that if you do this, by construction, f transpose theta will be 0 for all k. Fk transpose theta is 0 for all k, which means that the information matrix here will be singular. But if the matrix is singular, you cannot estimate theta. So here it's not, of course, it's not a problem here because we say theta is known, so we don't need to estimate it. But in practice, it's not like that. In practice, what one usually do is we use certainty equivalence control, which means we use the same form for u, but we replace the unknown theta by the current estimated value of theta. So, but if you use this, because theta is not estimable, this will not work. So you need to do something else. And what is done is that you add some perturbations to guarantee that the estimator will be consistent. And then if the estimator is consistent, then we use this u, then it will be fine. But you need to add these perturbations. So how big can be these perturbations? Assume you use what is called a persistently exciting input, which means that the normalized information matrix tends to some constant matrix. Yes? It means that when you consider here the unnormalized information matrix, it will be such that its minimum eigenvalue will grow like n. But then you have this property here that says this. So if the minimum eigenvalue of the matrix grows like n, it means that Rn divided by n is bounded away from 0. So if you have a persistently exciting input, it cannot be globally convergent because Rn divided by n will be bounded away from 0. So this type of problems has motivated a lot of work in the literature in adaptive control, and in particular by Lai and Wei, and they have obtained this type of results that they show that the minimum possible regret grows at least as log n. You cannot do better than log n, and they have suggested some control strategies that permit to achieve this rate of growth for Rn. But you see that here the situation is quite different from previous one, because here you really have some statistical problems, and here everything is related to the asymptotic properties of the least square estimator here. So we will say something now. I will say something about the asymptotic properties of the least square estimator. So least square estimator in regression models. So we use least square, that is, we minimize the sum of squares of differences here, which I denote Sn, And the conditions for the strong consistency of the least square estimator depend very much whether the design sequence, the sequence of design points, or the input sequence in case of a control problem. If the sequence is deterministic, it's a sequence of constants, or if depends on the disturbances, on the sequence of disturbances. Yes? So in the first case, where the design is deterministic, in the case of linear regression, there is a well-known necessary and sufficient condition for the strong consistency of the least square estimator. It is simply that the minimum eigenvalue of the unnormalized information matrix tends to infinity. This is necessary and sufficient. In nonlinear regression, so I define by dn this function. So this is the sum of squares of differences between the responses at two different values of theta. And there is a rather old but very well-known paper by Gendrich that says that if dn divided by n tends uniformly in theta to some deterministic function that is continuous and such that it is positive for when the two values of the parameters here differ, then the least square estimator is strongly consistent. Okay. So what does it give in a linear model? If we consider a linear model, this condition says that it's equivalent to saying that, well, it implies that the normalized information matrix will tend to some constant matrix, which corresponds to what is called the persistency of excitation. But if you have this, of course, this is much stronger than this. So it seems to be too strong. And one would expect, if we just want this, one would expect something like that. So simply the function dn here tends to infinity when the two values of the parameters are different. But this is not sufficient. So Jeff Hu has shown that this is sufficient when the parameter space is finite, but in general it's not sufficient. It is necessary under some additional conditions for the existence of a weakly consistent estimator, but it's not sufficient. Okay. So now what do we have when the design points depend on the sequence of disturbances? In linear regression, Lai and Wei have obtained a sufficient condition, which is the minimum eigenvalue of the unnormalized information matrix should tend to infinity. So this is necessary and sufficient when we are not in this situation, but here we have this, and moreover, the maximum eigenvalue should not tend to infinity too fast compared to the minimum eigenvalue. And in fact, their conditions are almost necessary in the sense that they show an example where this is just slightly violated and the least square estimator is not consistent. In nonlinear regression, so Lai has obtained a sufficient condition, which is rather complicated, so it's easier to look at what it gives in the linear situation. In the linear situation, his condition would be that the same thing, the minimum eigenvalue of the unnormalized matrix tends to infinity, and the maximum eigenvalue doesn't grow too fast. And of course, it should grow, it can grow faster here than here, of course, because the condition is more strict in the nonlinear case. Okay, so this is what he has to take. And these results here have been used in adaptive control. For instance, when I say that Lai and Wei have shown that the minimum regret grows like that, and they have constructed these input sequences that achieve this rate, is when they use this type of results. And this type of result here has been used in sequential design, as we shall see now. So, sequential optimal design. So we have a regression model which is nonlinear in theta, and then we know that the optimal design depends, the optimal design for estimating theta depends on the value of theta. So we have the information matrix that takes this form. F theta is the derivative of the response with respect to theta. Xi is a probability measure on the design space, and the d-optimal experiment maximizes log determinant of this. So I shall consider full sequential design. So first we select some design points, N0 design points, and then starting at N0 we work sequentially. We suggest a new design point, we observe at the design point, we re-estimate theta, and we suggest a new design point, and so on. So how do you suggest design points? Well, we want to maximize the determinant of the information matrix. So the idea is to look one step ahead, and xk plus 1 maximizes the determinant of the next information matrix. So this one, yes? Maximizes with respect to x. And of course here everything is evaluated at the current estimated value of theta. So it is forced certainty equivalence control. Doing this is equivalent to doing that, and here you recognize the D function in the Kiefer-Wolfowitz equivalence theorem, so you simply maximize this. Here again everything is evaluated at the current estimated value of theta. So we do that. But when we do this, we hope that the estimated value of the parameters will tend to the true value, and because everything is based on the information matrix, yes, everything is based on M, which by the way is not the information matrix because the design is sequential, so this is a random matrix because the design points are random variables inside. But okay, because everything is based on this, obviously we hope that asymptotically the estimator will be distributed with a covariance matrix which will be proportional to M minus 1. Yes, this is what we hope it will be like that. But how to prove that? So this is not easy. We can use three approaches. For instance, using the result I mentioned here, yes, using this type of result, we can, for a subsequence of k, we can use a deterministic choice of for xk. So sometimes we forget about the sequential construction and we force xk at some point. And if we do this often enough, then it will work because we can use the result I presented just before. Okay. This is the first possibility. A second possibility, which is, in my sense is not honest, but is because I said you choose first the N0 design points. Okay, let's N0 tend to infinity and then it will work. Well, it seems like a joke, but you find this in some papers. Then it works. And a third possibility is to suppose that the design space is finite. So why does it help? Simply because if it is finite, then necessarily you will have some replications of observations. And even if the design points are chosen sequentially, in the fact that you have replications, it helps very much to prove the strong consistency of the estimator and so on. So if we assume that we can choose the points only in a finite set, then about consistency, everything is fine if the function dn I defined previously grows to infinity fast enough when theta bar is different from theta. And when I say fast enough, in fact it's not very fast because something growing faster than log n is enough. So in this case it's easy to obtain what we want. Okay. About asymptotic normality, it's a bit more complicated because, as I say, the sequence of design, the sequence not of design matrices, well, the sequence of design matrices, yes, not information matrices. I can say design matrices because it's not precisely defined. So the sequence of matrices M here is a random sequence. What we need is to be able to renormalize this sequence by a sequence of deterministic matrices such that their minimum eigenvalue doesn't tend to 0 too fast. If we can construct that, then we will have the asymptotic normality of the estimator. And if we apply that to the sequential construction of the optimal design, then everything is fine. We have the strong consistency of the estimator. The sequence of design matrices converges to the information matrix for the d-optimal experiment, and the estimator is asymptotically normally distributed with the right covariance, with the right asymptotic covariance.
This is the finite.
Yeah, everything here is for
You're still within.
Yes.
You're still within that. Yes. Thank you very much.
Yes, yes, yes. Otherwise, I don't know. Now, penalized the optimal design. You will see why. You will understand later on why I'm interested into that. So now we want to construct a de-optimal experiment. We maximize log determinant m, but we set a constraint on the design. The constraint is with this integral form, and so small phi here can be understood as the cost of performing one observation at a given x. So this is a concave function of xi. This is linear in xi. So it's not a surprise that we can write a necessary and sufficient condition for optimality in this context, and it means that there should exist some Lagrange coefficient satisfying some properties. So this is not very important. We can write it. Okay. What is more interesting that in practice, how to solve this? Well, we simply consider this type of criteria here, and we consider this for an increasing sequence of lambda. You start with lambda equals 0, so you forget this. You simply construct a de-optimal experiment. If it satisfies the constraint, you're fine, the problem is solved. If it doesn't satisfy the constraint, you increase a little bit lambda and you try again. Yeah? And the first lambda for which the constraint is satisfied gives the solution. Well, of course, in practice, you will never do that. You will work by dichotomy. You will try lambda equals 0, then lambda very big, and okay, one is too small, one is too big, and then you will. Okay. But in any case, the problem is not more complicated than the solution of a sequence of de-optimal design problems. Okay. Here, everything depends on theta, so we can try to find the optimal design here sequentially. So the sequential construction in this case is the following: I have the same thing as previously, but I have this additional term here. And again, under the assumption that the design space is finite, for this type of construction, we have the following. If lambda is constant, then we still have strong consistency and asymptotic normality. And well, if we make further assumptions on phi, we even have that the sequence of matrices tends to the optimal matrix for this criterion here. Yes, so the same type of result that we had for the optimal design, because lambda is fixed. So we simply it is a simple modification of the de-optimality criterion. So it's also true if not if lambda is fixed, but if lambda is a bounded measurable function of all the past of the system. More interestingly, we can let lambda increase to infinity. Look in this construction. So we have this construction now, but we let lambda increase. Yes. So we put more and more weight on phi. And if lambda doesn't increase too fast, then we still have the strong consistency of the estimator. And moreover, in that case, the average cost here will tend to its minimum value. And if the function phi has a unique minimum in the set capital X here, if it is minimum as a unique xi star, then all the mass would the mass at xi star will tend to 1. All the mass will tend to concentrate on the minimum of phi, which means that we can minimize a function like that even if we don't know theta. So by this construction here, we have what is called a self-tuning optimizer. So we can minimize this function simply by using this sequence.
Your xk plus 1, is that sequentially, or is there any update algorithm you can have, or you do this every time?
Sorry?
X?
Yes, this constructs a sequence of x. Yes?
So we need to solve problem over again, or we can do some update algorithm to get...
Yeah, this is a very simple algorithm. This gives the next point. I update the matrix because I have a new point. I have a new regressor, so I update the matrix and so on.
I think my question is will be xk plus 1 be the function of previous xk?
Yes. Yeah, it depends on previous xk. It depends on the observations. So everything is random here. Yes, because you construct a random sequence, but that has these properties. So this had been suggested in the literature on adaptive control by Ashram and Wittenmark a long time ago, but they didn't give any condition for the consistency. And in fact, they even suggested, they implicitly suggested to take lambda k equal to k, which means that it doesn't satisfy the condition there. So I think their suggestion didn't work, but they had the idea. This type of idea was already there. And some years ago, I obtained results on this, but in the case where we had a linear regression model. So this doesn't depend on theta in that case, and just the function phi depends on theta. Of course, it's easier. So here we have a result even in a non-linear, in the case of non-linear regression, but I have the restriction that the design space should be finite. Okay, and we should be careful because the naive method would be to put next point at the minimum of the function, yes? Which is sometimes called best intention design, and this in general doesn't work. Or some examples. I will go directly to my second example here. So this is the example. So this is the regression model. So it's a nonlinear regression model. I have two parameters. And the objective is to find the value of x such that another function of x and theta, which is this function now, is set on some target t. This is to show that with this we can solve what is called self-tuning regulation. So we want to put a function to some value or some minimization problem, because in fact what we simply do is we transform this into a minimization problem, because we will minimize the quadratic distance to the target. Yes? So this is how I observe, and this is what I want to do. I want to minimize this. So note that we don't observe the function psi, huh? We observe something else. If we observe phi, of course it's simpler, but here we observe something different. So I'm considering this sequence here, this construction, and as I say, lambda should increase. I consider three different possibilities. It increases as log square k, like this or like that. And we remember that I had a condition on lambda k, which was, the condition was this, yes? So of course it should increase slower than k, which means that here, this violates the condition. So what do we get? So this is the type of results we obtain for the three sequence. So this, as a function of k, or it's a function of n here, sorry for the notation, but and here is the function I want to put on the target. So the target is the red line here, so I want the function to be set on the target. So in the last case, lambda is increasing too fast. It clearly doesn't work. So this works, it goes very slowly to the target. This seems to work a little bit better. So this lambda k is increasing faster, but this is just to show that we should be careful, because it increases faster, but on the time horizon that is considered, this is always smaller than this. So in fact, this increases slower, but on this time horizon, this is faster than this. Okay, so you should be careful. So this seems to work, and but you note. So we know that the mass will concentrate on x that gives points on the target, but you see that sometimes we put points far away. Yes. So we put some points there, some points there, some points there, some points there. Yes. And if we go on like that, if we look on the larger horizon, then you will put less and less points here and more points there. Yes. But still, you will still put some points there. So if you don't want to put points there, you simply need to change the penalty, to change the function you want to minimize. So if you put more weight on points that are far away from the target, so you change the power 2 here by a power 4, then you obtain this type of behavior. So this is a sequence phi, this is a function you want to set on the target, and you see that after some time you stop putting points far away, and all the points tend to be close. Yeah? So this is a sequence of design points. The optimum is when x is around 2 here, and so after some time you put all the points around the optimum. Okay, so this is all I think for the example.
So, did you say they actually get there in the...
Well, this is asymptotic convergence, so you
Yeah, they look awfully flat towards the end. Don't they?
yeah, yes, if you
It
you're
finishes
patient
far
enough,
away.
yes. So now I would like to say something about a different issue, which is different but related to the first part. It concerns design with dynamical constraints. So we have already seen problems like that in the first part. You remember the finite impulse response model, where the regressor is a shift register for the inputs. The Box and Jenkins model, where we have a sort of regressor which is obtained by a filtration of the input. So in both cases, we have regressors, we have a design matrix, but we have some constraints on the regressors. We cannot choose them as we want. So here I will consider a simpler example. Well, not really simpler because this is nonlinear in X. So it's okay. But it is a static. It's a purely static problem. Yes. So this is a linear regression model with two parameters. It's a quadratic function of X. I consider this design space, which is always included in -1, 1, but the lower bound underscore X will vary. I will consider different choices, and we obtain different designs depending on the lower bound here. For instance, if the lower bound is close to -1 or close to 1, then the optimum design puts half of the mass at underscore X and half of the mass at 1. Okay. If X is close to the center, but a little bit on the left, then the optimum design will put half of the weight at 1/2 and half of the weight at 1. Notice in particular that this interval, that this includes a case where the design space is 0, 1. When the design space is 0, 1, then the optimum design is this one. And there is also a third case, which is when X underscore is in this interval, then the optimum design is a 3-point measure. But okay, this was surprising for me, but it's not very interesting here. I'm mainly interested in these two cases. Okay, so we have this for this design problem. Okay. Now suppose that the design space now is -1, 1. We want to construct a d-optimal design on -1, 1, so it's not too difficult. But I'm using this algorithm. So this is Henry's algorithm from 1970. Henry was very young at the time. So this is a regressor. So I'm constructing this, and we know it's converging. So everything is known about that. Okay, this is fine. But assume now that I put a constraint on the design point. So I cannot move from one point to the other one because otherwise it's easy. I think the algorithm we choose sometimes -1, sometimes 1, sometimes -1, sometimes 1. It will, and at the end you will have the equal weight on both, and it will be fine. But here, assume that you have this constraint that you cannot move a lot. So either you stay at the same place, or you move a little bit on the left, or you move a little bit to the right. That's all. You can do that. And assume that you use a naive implementation of that. It means you use the same algorithm, but you force, when you choose your X, you choose your X with this constraint that X can be, the new X can be X minus delta, or the same, or X plus delta. Yes? But you use the same idea. So what do you get? Well, there is a strange thing that you realize that if X is equal to 0, then f here is a null vector, so the function here will be 0. So you will never choose such a X, because it is 0. So it will never be the maximum of the function. So if you start at X equal 1, if you do this, you will never cross 0. So even if the design space is -1, 1, you start at 1, you will never cross 0. So you are exactly in the same situation as if the design space was 0, 1. And in that case, the best you can have is this design. So the best you can hope here is to obtain this design. But do you obtain this design? Well, in fact, log determinant m as a function of k behave like that. So and there is no convergence. You will have some oscillations like that forever with a frequency, with a decreasing frequency. So you have, it will be slower and slower, but it will oscillate like that forever. You can compute the lim sup of the value, and the lim sup is indeed the optimal value that you can have on the interval 0, 1. But there is a lim nth, which is strictly smaller, that we can compute in this case, and so on. So it doesn't work. You have this behavior. It simply doesn't converge, and the lim sup you have is the best you can have on the interval 0, 1, not on the interval -1, 1. Second possibility, because this one doesn't work, is to directly solve the optimal control problem, because now x depends on u, and I will optimize with respect to u. So we set some constraints. For instance, we start from x equal 1. We say that after n steps, n given, we want to be at x equal -1. We put a constraint on the power of the input sequence, and we maximize the log determinant of the information matrix with this constraint. So we can do that. This is simply, this only depends on the UK. So we solve this. This is a constraint optimization problem. So direct optimization is rather complicated if n is large, because it becomes to be a high dimensional problem. But if you write down the optimality conditions, then you realize that the optimal input at step k is just a linear combination of xk to the power j from j equals 0 to 3. So in fact, you just have 4 parameters to, you just have to solve an optimization with respect to 4 parameters. So whatever the value of n. And this is what I did here for n equal 10. So we start from 1, we arrive at -1. So this is the evolution of x as a function of k. And it is the evolution of u as a function of k. And you see that x, because the problem is completely symmetric with respect to 0, so of course the trajectory of x is symmetric with respect to 0. But even this problem here, we just have 4 variables. Maybe I was not very clever when I tried to solve it, but I found it was not that easy to find a solution here. And now there is a third possibility. We can use a very heuristic approach, because on -1, 1 we know the optimum design. Yes, we should be at -1 half of the time, and at 1 half of the time. So because we start at 1, we know we should stay at 1 long enough. Then we should go quickly to -1, and then we should stay at -1 the rest of the time. Yes? And this is very naive, maybe, but of course we can compute the power we spend when we do that. So this is rather easy to do. Okay. So my sort of recommendation here, that maybe for such problems it is interesting to try to treat separately the design problem and the control problem. So here, of course, this was just an algorithmic problem, because this was a linear regression problem. We had, I mean, the sequence we construct doesn't depend on the estimated value of the parameters and so on. But in a nonlinear model, the information metric depends on theta, then we need to be adaptive, and we have mixtures of algorithmic and statistical problems. It's not easy. The fact that the design space is finite might help, but in any case, I think it's probably interesting to try to treat the two problems separately. Okay. Yes, I still have some minutes. I would like to consider the same type of problems, but in a completely different context. In the case of model-free design. So this corresponds to, for instance, to computer experiments, but there are some other types of of applications. And assume, for instance, that the problem is to construct an approximation of a function on the d-dimensional hypercube. You have no idea of what is the function. So, of course, you would like to observe almost everywhere. So you would like to spread the design points over the hypercube. And for instance, we can use for that maximum optimum design, which means we maximize the minimum distance between two design points in the cube. So in dimension 2, if you put 10 points, for instance, this is a possibility. So you put the 10 points like that. The design points are the red square here in the red small squares in the big red square, and we try to maximize the minimum distance between 2 points, and the circles here have a radius which is equal to half the minimum distance between 2 points. Yes? So this is the type of design you want. So you want to do this design, but assume that you have a dynamical constraint like that. So you can move from xk to xk plus 1 step by step. Yes? And if the cost is related to the length of the route you make, of course, the optimal solution corresponds to solving a traveling Salesman problem on the x on the design to find the shortest route on the design point. So we have to, for instance, this route here. Yes? This is the shortest route on the design. So in that case, you will have problems like that. Yeah? And there is an interesting property here. This is a very old result, well, a rather old result by Bernoud, Halton, and Hammersley. They're saying that if you have a PDF file and if you generate with this PDF points in the unit cube, and you construct a traveling Salesman, you solve a traveling Salesman problem on these points, then the sum of the edges of the graph you obtain, so the sum of the edges here of this graph, this is a graph, yes. So the sum of the edges there, suitably normalized, tends to some integral of phi. So this was a surprising result for me, at least, and this has motivated a lot of work concerning some other functionals on X than this one, than the traveling Salesman graph, in particular by Yukish using a property of quasi-additivity. And so a lot of people have worked on that, and they have obtained very nice results of the same type for many different graphs. I mean, you can have, for instance, the minimum spanning tree, the nearest neighbor graph, Voronoi, Delaunay, a lot of graphs have this property that if you take the edges of the graph, the length of the edges to some power beta, you normalize suitably, and this converges to some integral of phi, which is the PDF that was used to generate the points on which you construct the graph. Yes? So why I'm mentioning that? So we have this property. Now, if you think about the Renyi entropy of phi, so this is defined here, you realize that this is simply proportional to the Renyi entropy of order 1 minus beta divided by d. And this type of properties they hold in particular when beta is between 1 and d, which means that here alpha is positive. And when alpha is positive, the Renyi entropy of order alpha is maximum for the uniform distribution. So because I said at the beginning that we want a space-filling design, that we want to design so that the design points are spread in the space, we want the design point to be uniformly distributed because we want them to be everywhere. Yes? So if we want a uniform distribution, so because of this property, we want to maximize this. And because this tends to that, of course, we want to maximize that. So if we come back to the traveling Salesman problem, it means that we want to find a short route among the design points, but a good design is a design for which the route is long. So in any case, you know that you should be prepared to spend some money. Yes, because the long route corresponds to good designs in terms of space filling. So this is the case where we only make observations there at the design points. Yes. So which type of design do we have if we observe also along the route? Assume that we observe continuously along the route. So then it's not this type of design that we shall have. So maybe something like that is more interesting, because then if you have something like that, you know that you are never very far from a point where you have made an observation. So I don't know, you will have some space filling curves and this type of thing. So this is completely different issue, but of course it's connected to this topic. Okay, so it's time to conclude. I just have one slide for conclusion. So we have seen that input design for dynamical systems is a control problem. We have seen that adaptive control, self-tuning, optimization, regulation, and so on, is more related to statistical problem about the consistency of estimators. So it's very much connected to design problems. Sequential penalize the optimal design gives us a method to solve some adaptive control problems. We have some results about the asymptotic properties, like consistency of the estimator, asymptotic normality when here lambda is bounded. When lambda tends to infinity, not too fast, as I said, it's useful for some adaptive control problems. But all these results here assume that the design space is finite. And it's not clear if this is absolutely necessary or if it's just a technical assumption. I think that more work is required there. When lambda tends to infinity, I was not able to obtain the asymptotic normality, but my feeling is that if it tends to infinity slowly enough, we should have also asymptotic normality, but it's more difficult. And the last thing was about dynamically constrained designs, where we cannot choose a sequence of design points as we want. There is a dynamical constraint in the sequence of design points. And my feeling is that it could be useful then to separate the problems and to first to construct an optimal design and then find a way to visit the optimal support points, one after the other. Yes, that's all. Thank you.
And on to discussion.
Yes.
Look, I'm curious about your model-free design, about max-min design. If you apply that to large enough Q, for example, within the class, of course, the X will be finite, for sure. And would that be, with the result you think will be applicable over there, or?
Well, you can consider light in happy cube a maximin optimal design. Yes, you can work in this class, but well, I simply mentioned that if you have to visit the design points, then you have to find the shortest route through the design point. This is whole.
Any other questions? Hakan?
Thanks for a very interesting seminar, Luc. You look at this one step ahead horizon. So have you thought anything about going a little bit further into the future?
No. It's difficult to say because there are two conflicting things. Look, in terms of the construction of the sequence of points, it's probably interesting to look several steps ahead. Yes? Because you think that you will get a better performance if you look several steps ahead. But in terms of adaptivity, it's the opposite in the sense that it seems useful to use all the information you have at each step. And the information you have is the current estimated value of the parameters. So there are these two conflicting things. So maybe at the beginning, one step ahead is better. And once you know enough about the parameters, maybe then it's better to look several steps ahead, things like that. But I have no idea, so I didn't try.
Henry?
Slightly different version of that is to do batch. So you do
Yes.
n at each step. So maybe the asymptotics gets easier if you take the batch as larger.
Yes. If m is larger than the number of parameters, then it's fine.
Manuel?
On the sequential design, how did you select the very first parameter estimate with respect to which you compute the information matrix?
Well, it's not very important because because the system will adapt. So it's not very important. But well, of course, if the closer you are to the true value, the better it is. But I think it's not a crucial issue because
it's no prior over parameter space. Also, a second question on the sequential design. If you could bring up the slide, maybe. When you define your design criterion, if I understood it right, it's only on the information matrix of the next experiment as a proxy for the posterior covariance after that step. Is that right?
Which?
The first one on the sequential.
Or the first one on the sequential should be
Just in the beginning.
before that. Sorry. No.
Yes, somewhere there.
Somewhere there. Yeah. This type of thing.
Yes. So there, your design criterion.
Wait.
Yes.
I know. This one. Yes. Oops.
Yes, with the design criteria. So, is that
That just this is one step ahead. This is a current design matrix. At the next step, you will have one more, yes, well, one additional regressor evaluated at x. So this is the next matrix, and you maximize the determinant of this.
okay? So you try to maximize the determinant of the full
Yes.
posterior covariance matrix,
Yes.
considering all previous.
And this is the same as that. Yes.
Okay.
Thank you very much, Luc.
Thank you.